So in this second section, we'll be essentially going through the properties of fluids and something called as the continuum approximation. Here is just a brief outline of some of the topics we'll be covering. Like you mentioned, we'll do a continuum approximation, talk about it, mention some of the differences between extensive and intensive properties, talk about viscosity and surface tension, the two properties associated with fluids that are different or new compared to solid, some of the properties of solid mechanics that you're familiar with. And then essentially last part will be classification of fluid flows. We'll just discuss on the two big ones that you will be encountering throughout the class, which is steady versus unsteady flows and laminar versus turbulent flows. Okay, and finally we'll be going over some of example problems related to this chapter. When it comes to the continuum assumption, right, so this is an assumption that is not specific to even fluid mechanics. It's something that probably you have always made in any physics or mechanics problem that you have ever solved without realizing even the fact that you're making that assumption, right? So when you talk about continuum, when you're talking about continuum assumption, right, it is essentially saying that any property or any parameter of associated with a material, so let's say its density or its mass, you can say the yield strength, the velocity, the forces or stress distribution, any property or parameter that is associated with a material, you're assuming it to be continuous, right? That is an approximation often, and that's an approximation because of we are making to make our lives simpler, right? And it's a pretty useful and true approximation, but you have to be mindful that since it's an approximation or assumption, in certain cases that might not still be true, right? So you should be the whole point of knowing the assumptions or approximations so that you know up to what extent is it true or not true, right? So essentially I think so best this is explained by an example. So what I'll do is I'll go to the next slide and kind of describe. Okay, so for the example, let me say if I take a piece, okay, perfect. So if I take a piece of material, and let's say this is a rectangular piece of material that I'm looking at, and if I say this material has a density of 1 kilogram per meter cube, right? So if I'm talking about this material, right, so now in this material, if I ask you, okay, I'm only going to look at a section of this material, so let's say this tiny section, and if I ask you what is the density of this section, you would say that this is 1 kilogram per meter cube, right, considering if it's a uniform and isotropic material. Okay, now to make things more clear, let me just change the color of my marker pen, right? Now if I say, okay, if that's the case, if I reduce this volume that I'm looking at and reduce it to this tiny bit, right? Now if I go out in this tiny bit of space, what is the density? And then you will say it is still 1 kilogram per meter cube. Now for argument's sake, if I say like, okay, let's say if I reduce it even further so that the volume that I'm looking at is just a point, let's say that blue dot right there, and if I ask you what's the density of that dot, right, then you'll again say that it is 1 kilogram per meter cube, right? But the question is, so if I keep on reducing this volume that I'm considering of or looking at of this material, or section of this material I'm looking at, or area of the material I'm looking at, if I keep on reducing it forever, will my density always be 1 kilogram per meter cube? And the first thing that will come to you as students would be, yes, it is, right? And that fact that you're saying that regardless of what volume that you use, it will be 1 kilogram per meter cube, is something coming off of a continuum assumption. That you're saying that any point you see, no matter how small the volume it is, the material property is going to be uniform and the same, right? But that is an approximation, and I try to explain you why. Right. So when it comes to density, right? How do you get density, right? Density is nothing but total mass divided by the volume of the system that you're looking at, right? So now if you're saying mass, okay, you can measure volume directly. How is mass constituted? How do you get mass of a system that you're looking at, right? Mass is nothing but the number of atoms that is there in that system times the molecular weight of the atoms that are there, right? So that constitutes the mass, and then you divide it by volume, you get the density. Now if I'm considering X dot that we made here, right? And if I say I want to zoom into it, so I zoom into that dot, so you have this dot that is here, I'm zooming it for clarity, and then essentially in that, when I zoom into it, now I can see actually the lattice structure, right? So let's say if this was a solid and it is made up of atoms that are roughly uniformly spaced, right? So essentially the mass of this dot is essentially, you add up the molecular weight of each atoms, right? So that's the number of atoms that is there times the molecular weight, right? So here is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So that will give you the mass, and then you divide it by the volume that this spatial space occupies, right? Now if this is the case, so hopefully that is clear, what happens if when I picking this dot, or if I pick even a smaller dot here, right? So if I pick a volume of interest, okay, this yellow will not do because I'll change the color, sorry. What happens if I pick a volume of a system that is in between these atoms? So I pick it so small such that it is actually smaller than the atomic spacing, and then I say what's the density of this material that we have been talking about in this system we are considering, right? In theory, when we talked about previously, we said like no matter how small the volume is, even if it's a mathematical size or goes down to mathematical point, you still are saying the density is 1 kilogram per meter cube. But now when you look closely, you see that in this case, if you start looking at what is the number of atoms that you have 0 atoms here, right? And what is the molecular weight, right? So the molecular weight will still stay the same, but you have 0 atoms, and then you have a finite volume. So essentially, since you have 0 atoms, you have 0 mass, right? So your density will come out to be 0, right? So essentially, this continuum assumption that you're making of the density always being 1 kilogram per meter cube is an assumption, and it is only valid when the system size, right? So the volume or size of the system that you're considering is much bigger. So it's much bigger than atomic scales or atomic lengths. right? So if if it's starting to be comparable to atomic lengths, then you cannot make this assumption anymore, right? So you cannot just blindly say, oh, since the density was given to be 1 kilogram per meter cube, it will, even in this small volume, it's 1 kilogram per meter cube. And the reason I'm bringing this up is just so that you know that this is an assumption you're always making, right? So if you're doing research, or if you're doing if you go ahead in future and look at practical some problems, so for instance, if you're talking about nanotubes, right, or if you're looking at thinking of literally molecular scale material patterns or density, right? So at that point, if you're talking about even nanofluidics, right, your volume of the system that you're looking at, you're saying that is at nanometer scale, right? And the atomic scales are roughly an angstrom scale. So 10 to the power of minus 10 is your atomic scales. So atomic length scales are 1 angstrom, or roughly 10 to the power of minus 10, so approximately meters. While if you're looking at a problem of related to nanotubes, or sorry, let me fix this. Since I was running out of space, I decided to just use a new slide. So if you're talking about atoms and the length scales of atoms, right, so atomic length scales are generally of the magnitude of 10 to the power of minus 10 meters, or 1 angstrom, right? So if the system volume or length scales of the system that you're looking at, so length of system is roughly comparable, or if it is, so it's roughly comparable to this atomic length scales, you cannot make continuum assumption, right? So that is the main criteria, right? So for instance, if you're looking at a nanotube, right, nanotube by definition means that the diameter of the tubes that you're looking at is nanometer range, right? So the diameter here you're looking at is, let's say, approximately 10 to the power of minus 9 meter, right? So that is not much, this is not much less than 10 to the power of, oh sorry, I should say, my bad, I need to fix this. Sorry, so this is not much bigger than 10 to the power of minus 10 meters, right? So this nanometer or diameter of this nanotube is comparable to this, right? So if the volume or the length scales of the system you're looking at is not much bigger than this, right, which is the case in this, you cannot make continuum assumption. So continuum assumption does not hold true, right? So this is the reason you should be aware of this limitation. So if you're working at length scale that are so small, right, you have to be mindful that you can't say that the property is uniform throughout, or if every parameter that you're looking at is going to be consistent or uniform, right, because you're getting comparable to the molecular length scale. So just something to keep in mind. On the flip side of this is, right, what happens, so this is when you're saying the molecular length scales are 10 to the power of minus 10, right? But if you are, let's say if I give you another example. Okay, for a second example, for where this continuum assumption might break down, is let's say if you're talking about re-entry of a spacecraft, right? Let's say the space shuttle or a rocket component. And if I'm talking about a sensor that is placed in the space shuttle or a re-entry vehicle, So let's say that sensor is the size of 1/4 inch, let's say, for argument's sake, right? Okay, now if you look at normal length scales of atoms, right, we already mentioned we are talking about the atomic length scales being 10 to the power of minus 10. But now we are talking about re-entry. So let's say you are literally at the edge of space, right, and you're just entering the atmosphere of the Earth, right? So here the atoms or the gases are very rarefied, right? So by rarefied meaning that the atomic spacing or the length scales of that is actually fairly big, right? So it is much bigger for that rarefied gas than 10 to the power of minus 10 meters, right? So it might there might be a situation where this 1/4 of an inch is still, because you are looking at a medium where the medium itself's atomic length scales are much greater and actually comparable to an inch or just a fraction of an inch, you are still comparable to the length scales, right? So as a result of this rarefied gas, your length scales of the sensor is still comparable to the atomic length scales, right? So as a result, again, you can't make the continuum assumption, right? So one is if your dimension of the system becomes very small, or the flip way to look at it, if your atomic length scales becomes fairly large, right? So in both of these cases, if your end of the day, if your system size is comparable to the molecular length scales, you cannot make continuum assumption. You have that continuum assumption breaks down, right? So that is something that you just need to be aware of and at least have a conceptual understanding. So the next thing we'll be covering will be extensive and intensive property, right? So this is a concept that is still, again, nothing limited to fluid mechanics, right? Any property of a material can be characterized or can be divided into two categories, right? It can be either said to be an extensive quantity and intensive quantity, right? So the way you decide an extensive and intensive quantity, right, by definition, right, an intensive property are the properties that are independent of the mass of the system, right, such as temperature, pressure, and density, right? Whereas extensive properties are those properties that depend on the mass or the size of the system. So I think something should be added here. It's not just the mass, but also the size of the system, right? And it's always best when it comes to these to look at examples, right? So let's say if you pick one of the properties, let's say, let's start with mass. That's the most obvious one, right? So if I have this volume, and if I say the mass of this volume is 10 kilograms, right? Now, if I change the volume of this system that I'm looking at, so let's say if I divide this volume into two, right? So that's kind of what this illustration is saying. If I divide it and split it into two parts, now will this mass that I'm considering be the same or it will change, right? So if it is changing, right, so the mass of this will no longer be 10, right? If I split it into half, you can say that, okay, this mass is going to be 5 kilograms, this mass is going to be 5 kilograms, assuming uniform density, right? So in that case, if that property is dependent on the size or the mass of the system, then it's an extensive property, right? So that's extensive property. So mass becomes an extensive property. Same comes with volume, right? So if you divide volume If you take half of the system, then obviously the volume is going to get half. So that is an extensive property. But now if you excuse me. But now if you look at quantities such as density, right? No matter how I divide this volume, right, the density will remain constant, right? So it is independent of the volume or the mass of the system. So it's an intensive property, right? When it comes to pressure, right, how is pressure defined? Pressure is force over area, right? So if you say this is a flat plate, right? So let's say this wall, instead of volume, let's say you're looking at surface and this is a flat surface. If you're applying a uniform force on this across this cross section, and if I ask you to find the pressure of this total on this total cross section, you'll divide the force by area, right? Okay. Now, if I divide the system that you're considering into two, okay, and ask you what is the pressure on this half only, will the pressure change or reduce? Right? Since it was uniformly distributed, your force acting on this is only half of the total force that you initially had. But the area also is now only half of the initial area, right? So if you find pressure, you see these two quantities get divided, half and half goes away, so pressure will still stay the same, right? So pressure as a result an intensive property, but then force, right, is an example of an extensive property, right? And then similarly you have temperature. So when it comes to extensive and intensive properties, right, best way that I suggest students always to decide if a property or a quantity is extensive or intensive is just think about in your head, if I'm looking at that property and if I assign that a value to the to a system for that property, so let's say density, velocity, right, and then if I divide that system into half or make it twice bigger, will that value change or be the same, right? So if it's density, for example, if it's like density what we talked about, that value is not going to change. If I say it's 1 kilogram per meter cube, it's going to say 1 kilogram if I double the volume or reduced it by half, right? So then it's intensive property. But if it is if you divide it and if it gets reduced, right, so then it's an example of an extensive property. Or if it gets multiplied, then it gets example, right? So always in your head, if I ask you a question of, if I throw at you a random property, just think about, okay, if I assign a value to a specific volume, now if I change the volume size, will this assigned value stay the same or different? If it's staying the same, it's intensive. If it's becoming different, then it's extensive, right? That's all you need to know from this. Okay, so when it comes to properties, right, so the most common property associated with fluid is viscosity. And the reason we focus on viscosity, because for other properties such as density, you're already familiar with that concept from solid mechanics, right? So viscosity is kind of new and unique to fluids in general, right? So viscosity is nothing but essentially is a result of internal friction or internal resistance, right? So it's a property that represents internal resistance of a fluid to motion, right? So essentially, if you're trying to move fluid, all right, if you're trying to move your hand through a fluid, or if an object is moving through a fluid, right, how much resistance will you feel? So if you, for instance, you're running at the same speed, but you're running in air, right, you'll feel certain resistance But now if you're running at that same speed underwater, you'll feel a higher resistance, right? Because the viscosity of water is much higher than that of air, right? So essentially that's all it is, right? So viscosity is just the internal friction or internal resistance given or provided by a fluid to motion itself, right? So when you talk about drag force, it's directly related to viscosity of the material itself. Right. So when it comes to viscosity, right, the relationship where viscosity is defined comes from the linear relationship between shear stress and velocity gradient, something that we talked about previously, right? So this is same as how in solid mechanics we talked about you have shear stress tau being proportional to shear strain, but in fluids shear stress, because it is constantly deforming, you're talking about shear rate, right, instead of just the strain. This is same as saying, this is also often referred to as velocity gradient. Sorry, I got that spelling wrong again. Right, so shear rate or velocity gradient or rate of deformation are essentially referring to the same thing, right? So when you're talking about shear rate, essentially that is defined as, trying to find a space to write. Shear rate is nothing but change of velocity over a normal distance. So essentially du dy in this case, right? So this is shear rate. So essentially when you're talking about shear rate, right, if you have two plates, right, so I think it will be better understood with this example. If you have two parallel plates with a fluid in between, the bottom plate is stationary and the top plate is moving with certain velocity, right? So what you'll see is, because of this gradient in velocity, you will see a velocity gradient develop, right? And this goes back to, if you're thinking about the example that we had shown of a video of cornstarch in a cylinder, and how when he was rotating, he was constantly deforming the liquid. As a result, it was constantly stretching, right? Similarly, that's essentially what is happening, but instead of a cylindrical, you just have two infinitely parallel plates, right? So this velocity gradient is generated because of one fact or one boundary condition called as the no-slip boundary condition, which is essentially saying that if you have a solid object moving next to a liquid, the velocity of the liquid right next to the solid will be same as that of the solid. So in this case, the velocity of the liquid right next to the solid is this velocity v, right? Now in the bottom plate is stationary, right? So as a result, the bottom plate, the fluid or liquid in contact with the bottom plate, is going to have the same velocity as the bottom plate, which is 0, right? So essentially the no-slip boundary condition says that a fluid is essentially in some sense going to stick to the solid object, right? So there's some friction, so it will, as a result of friction, it's going to move with the same velocity as that, and that creates this velocity gradient that is there, right? So this linear velocity profile, right? So essentially this velocity profile you get, it's a linear. So if you go back to basic math and you realize that a line of a linear line is given by the relationship y is equal to mx plus c, where m is the slope of that linear line, right? So similarly, using this principle, you can find the velocity gradient or the relationship or the equation for this line or velocity profile that is there, which is given as u is equal to y divided by the length of this channel or the height of this channel times the velocity at which this wall is moving, right, where y is the coordinate in y direction, right. So depending on different locations of y you can find the local velocity at different points, right. So point here, point y, if you keep on putting different y values. So this gives you a velocity profile, right. So what this velocity gradient is doing, or shear rate, is essentially it's the derivative of this in the y direction, right. So you're taking the derivative of this relationship, so you're taking du dy, which will give you that this, if you take the first derivative of it, it becomes velocity times L, right. So that becomes the shear rate. If you look at this more closely, right, and you compare with this relationship of a linear profile, you'll see this is nothing but the slope of this line. So this is the slope. The shear rate is nothing but slope of this line. So du dy is just going to be slope of the velocity profile, right. So given the velocity profile, you should be able to find the velocity gradient, right. Okay, so now how the viscosity comes into play is, you know that the shear stress is proportional to the velocity gradient or shear rate. Now in order to remove the proportionality sign, you can do that by adding a constant here, right. So if you add a constant, this proportionality sign becomes an equal to sign, and this constant is what is called as viscosity. So essentially this relationship mathematically ends up being this, right. So shear stress is proportional to velocity gradient and the proportionality constant is viscosity. So essentially, if you have moving with the same velocity, that is similar to how I was talking of the example of you running in air was underwater, right. So your velocity gradient, because your velocity is same, the distances, if you're considering uniform distances where you're measuring it, your velocity gradients will be the same. But now in air, your viscosity will be less, so your stress or force exerted or drag you exert, right, will be less in air. But now in water, this mu value is going to be high, assuming this du dy is going to be constant still or stay the same. As a result, the stress is going to be higher, right, because your viscosity increases. Now if your stress is higher, naturally your force is going to be higher, right. Your stress and force are related by just the surface area. So your area, that is, if it is constant, then stress times area is force, right. So if your stress is higher, force is higher, right. So you can see how this relationship comes into play, right. So this relationship is actually something that's very important relationship. So when it comes to fluid mechanics, right. So let me just highlight which relationship I'm talking about. This one in red, right. So this relationship is very important, and it is actually used in even calculating very complex forces or stresses, right. So if you're thinking about drag force that you compute even for an analytical problem or textbook problem to a very complex problem of a flow over, let's say, of a rocket or aerodynamics of a supersonic aircraft, right. The drag force is essentially a tangential force, which is part of the constitution, the force that constitutes a drag force is from shear or friction forces because of internal resistance, right. So what you see even in that, what you end up finding is the way the drag force is computed is first you find the local velocity gradient, then you know the viscosity, you multiply that by area, right, and then you get the force, right. So this relationship is a very common relationship and something that you hopefully that you remember, and you need to remember throughout the course of this whole semester, right? Okay, on the bottom you have the common units associated with viscosity, or dynamic viscosity is what it is actually called as. So this relationship also helps you define a type of fluid. So most fluids that you talk or look or consider are actually classified as something called as the Newtonian fluid. Essentially a fluid that follows this relationship, that shear stress is proportional to shear rate, or this equation, right? But that being said, there are other fluids which are more unique and which will be not covering in class, but it's something that you should be aware of, that do not follow this relationship, right? And those are called as non-Newtonian fluid. So the fluids that whose rate of deformation is proportional to stress is called a Newtonian fluid. So on vice versa, non-Newtonian fluid is fluids that do not follow this rate. So essentially, if you look at this, right, this relationship says the viscosity is constant, so you have this linear relationship lines, right, that you get, or linear velocity gradients, relationship between stress and rate of deformation. If this relationship is non-linear, then essentially you're talking about non-Newtonian fluids. Couple of non-Newtonian fluids, just so that you are aware of, you probably have encountered at some point. So this video kind of briefly covers and gives an example of non-Newtonian fluids and Newtonian fluids. And more generally, you'll see when you're talking about non-Newtonian fluids, it's generally non-Newtonian liquids that you encounter more. It's very rare to find, or it's hard to find, a non-Newtonian gas per se. Most gas follow Newtonian behavior. So here he is using the example of honey, right? So often people misunderstand Newtonian behavior with viscous liquids, right? So honey is a viscous, right, liquid, right? It's dense, it's sticky and gooey, but it's still Newtonian, right? Then the fact is, if you're applying a shear stress, or if you're applying a force, right, no matter what force you apply, it will still have the same viscosity, right? So it still flows kind of similar, like a liquid, right? So here he's putting a hammer, he's moving with a spoon, he's putting a ruler in. If it's put slowly or fast, it's still, the ruler enters it and it still behaves like a liquid, right? So that's kind of what it's meaning by a Newtonian liquid, right? So the viscosity is not getting affected by the stress or the force he applies, or the rate at which it applies, like the velocity gradient, so rate. But on the other hand, cornstarch is a non-Newtonian liquid. So if you move things slowly, right? So if you move your hand slowly among cornstarch, if you put this ruler in slowly, or next he'll show the example of a hammer, it will emerge and you can push it around as if it's a solid. But now if he's hitting that ruler hard or quickly, so essentially it's increasing the velocity gradient or shear stress or shear rate, you see he cannot push in, or the property or the behavior of that liquid changes. So it starts behaving like a solid. Right now, if he hits the hammer slowly, it can enter. Right, as soon as he hits it fast, essentially it's increasing the velocity gradient, so the viscosity changes. So the viscosity is a function, or is not a constant. It's a function of velocity gradient itself, right? So that's the whole point of a non-Newtonian liquid, that it does not stay constant. The viscosity can change and it's dependent specifically by changing. I'm saying the viscosity is dependent on the velocity gradient. So this is an example that you'll see people talking about for making fun videos of, people walking on a liquid, right? If he's standing slowly, his leg submerges, but if he does it quickly, he can walk or run on a liquid. There's a bunch of videos of people trying to even riding a bicycle on a cornstarch liquid, right? So that's kind of one of the examples that is there, right? This is another example of same cornstarch, right? But you think like, oh, what's the use of it? Is it just a fun experiment that people do for demonstration purposes, or there's actual practical applications that you can actually use for, right? So this is a group at MIT kind of demonstrating and trying to model this behavior. So here you can see, as long as he's moving his hands quickly, the cornstarch becomes like a ball. But as soon as he stops moving his hands, that is, he's reducing velocity gradient, it becomes like a gooey liquid, right? So one of the applications this group at MIT were suggesting was, if you think about, you have a pothole in road, right? If you want to quickly fix the pothole, can you you can use this liquid or a non-Newtonian liquid similar to this and pour it in that pothole. So as soon as a car passes, so it's very easy to transport, right? You can easily put it. It should be a quick fix for temporary fix, right? But if you just pour it, it's there, and as soon as a car passes over it, because it's applying a sudden force at the speed at which a car passes, it will behave as a solid, so it will you won't sink in, right? So it will kind of minimize the effect of a pothole, right? The other possible scenario they were looking at is liquids that have similar behavior, but it is application might be in bulletproof vests, right? So one of the issues with bulletproof vests, they're heavy, but also they're clunky. So it's like it reduces the agility of the person wearing the bulletproof vest, right? So if you're thinking about if you can make a bulletproof vest with a liquid like this, so it behaves like a liquid when the person is moving, because he's moving at fairly slow rates, right? So he can move around and it can be agile. But when the person is moving, let's say, if he is shot by a bullet, now the bullet is coming at very fast rate, right? So when a bullet hits the jacket, then this liquid no longer appears like liquid, it becomes a solid, and then it will block the bullet, right? So it kind of balances this act, right? So that's one of the applications of it. So here the cornstarch example was essentially of how the liquid becomes more viscous and behaves like a solid. On the flip side, there are liquids that on application of force that actually behaves more like a liquid, so its viscosity reduces, whereas if you don't apply force, its viscosity increases. And an example of this is quicksand. So you might have heard, if you fall into quicksand, you are told to try to stay as calm and stagnant as possible, right? Because in the case of quicksand behaves like a non-Newtonian liquid, but on the flip side. So if you move your hands, if you get panicked and move your legs and arms around, you are increasing the velocity gradient, and you actually ends up reducing the viscosity of the quicksand. So you start sinking more and more in. But if you are standing stationary, it behaves relatively like a solid, so you will not sink as fast as if you were moving around, right? So it's the opposite of it. So just something to be aware of, and an example that we want to give of non-Newtonian liquids. But naturally in this class, most of the examples or problems we'll be looking at will be all related to Newtonian fluids. So we talked about dynamic viscosity. Kinematic viscosity is not necessarily completely new quantity. It's just dynamic viscosity divided by density. So that's all you need to take away from this, that you need to at least know this relationship. So instead of dynamic viscosity mu, if I give you kinematic viscosity, you should be aware that it's just dynamic viscosity by density. So you can go back and forth if needed. So when it comes to viscosity, right, viscosity is temperature dependent, right? So when we talk about honey, right, or you might have thought about even oil or normal generic cooking oil that you're looking at, right? uh, if you heat the cooking oil or if you heat honey, you'll see that it becomes more liquid, or it moves more freely, right? By moving more freely, essentially you're saying the internal resistance of the fluid reduces. That means the viscosity has reduces, right? So essentially for liquids, right, viscosity decreases with temperature. But this is not the case for gases, and this is something that you need to be aware of. In the gases, because of how the interatomic atomic forces are weak, actually by increasing temperature you're increasing the kinetic energy, so it starts bombarding against each other more, which actually increases the viscosity. So in the case of gases, the viscosity actually increases with temperature. So this distinction you need to be aware of, right? So in the case of liquids, it's more intuitive. So that's one of the best ways I tell students to remember is remember what happens for a liquid, because you have so many tangible examples of it. So when you're thinking about liquids, you can think of an example of honey or cooking oil or something else, like, all right. So you can think of that example and say like, oh, as the temperature increases, the viscosity actually starts decreasing, right? And the way to remember for gases is that it is flip of that of liquids, right? So viscosity of gas actually starts increasing with temperature. Okay, so this you don't need to know the equation, but you need to know that it actually decreases. For liquids viscosity decreases with temperature, and be aware of the fact that for viscosity of gases actually increases with temperature. So essentially for gases, the internal resistance increases the higher warmer it gets, right? So let's say if you're talking about re-entry vehicle, as soon as it enters, there's so much friction and it comes at such high velocities at even Mach 20, Mach 25 speeds, that is gets really hot, right? So the temperature actually on the surface increases. So there the viscosity of that atmosphere, even though it's a very thin rarefied atmosphere, increases dramatically because the temperature is higher, and as a result you see more friction and more heat and drag effects as a result of it. So the next property of the fluid that I want to discuss is called surface tension. I'm pretty sure you guys are familiar with surface tension, or at least have heard it. But what I want to focus here a bit on is what is the cause of surface tension. What phenomenon results in a fluid on the surface having some tension, right? So this figure here does a decent job of explaining, so we'll kind of go off of that. So if you're talking about a fluid molecule, if you're looking at a fluid molecule in the middle of a fluid, right, or a liquid domain, right, and if you are looking at all the forces acting on it, now since the fluid molecule is embedded deep inside the liquid, it is going to be always surrounded by other fluid molecules in pretty much every direction, because of how densely a liquid is packed compared to gases, right? But regardless, even in gases, you'll have gas molecules always surrounding another gas molecule, right? So if you're concerned with this specific gas, liquid molecule or a fluid molecule, right, since there are other identical fluid molecules surrounding it and it's uniformly surrounding it, if you try to calculate the net force on it, you'll see that it will have a net force acting on it because from other molecules around it in every single direction, right? So it will be completely uniform for a uniform material, and specifically for a fluid molecule deep inside the liquid or the fluid. right? So this force is uniformly distributed, and that's kind of uh, what they're trying to signify in this diagram here, right? So as a result, if you try to find the net force acting on this fluid molecule, what will you get? Right? If you try to resolve all of the forces in normal and tangential component, you'll see the net force acting normally will be on, like, upwards and downwards will be equal, so it will balance and cancel out, and the same thing with in the x and y direction, right? So left and right direction, right? So essentially you will have zero net force acting on that because of how uniformly all the forces or all the molecules are exerting or interacting with that particular fluid molecule. Now if this particular fluid molecule moves to the interface or to the surface, where on one side you have air, or even if we want to make it simple, we can say vacuum for now, right? So if I take this fluid molecule and say, like, okay, it is such that it is right at the interface, we split halfway, and that's just for demonstration or to make this concept clear. What you see is now there is no fluid molecules or the same fluid present on the top, right? You have vacuum here, right? So there is none of these fluid molecules on the top. There's only fluid molecules at the bottom. So there is no force exerted or experienced by this fluid molecule from the top half of it, right? All the flows are concentrated. So if you try to now find the net force, you'll see that the net force, you'll have a net downwards force. So in the left and right direction, you'll still have an equilibrium, but there'll be a net downwards force, right? This imbalance of forces experienced by fluid molecules at the surface is what is causing surface tension, right? So that's kind of one of the key things, at least the key understanding I want you guys to take, is the imbalance of forces or imbalance of molecular or interatomic forces experienced by fluid molecules at the surface results in surface tension, right? So I'm assuming you guys have seen examples of, when people talk about examples, you talk about often if you have a glass of water and you start filling it up with liquid, you can go up to the brim, but then you can actually pour a bit more, which allows you to go above the brim, right? The reason you can hold or add more volume of liquid than the container itself is because of surface tension. Surface tension allows you to add that extra volume, and I can explain you how it works, right? So think of it, it's the best analogy I think of is as a balloon, right? If you have a balloon and if you fill it up with air inside, that will be at a higher pressure than the atmospheric pressure outside, right? Once you're filling it up, and that keeps this balloon taut and in a spherical shape, right? Now the question is, what is allowing you to sustain a higher pressure inside compared to the atmospheric pressure, right? I'm pretty sure everybody will realize or can say, like, it is this membrane of the balloon itself, right? So the membrane of the balloon, while this air is being filled and the pressure increased, is at a constant tension, right? It's very taut. If you try to squeeze on it, if you press on it, you'll see it will bounce back, right? It is at a tension compared to if the air inside was just the atmospheric pressure, then it's just flaccid, right? Once you fill it up with air and add additional pressure, this balloon itself or the skin or the membrane of the balloon goes into tension. So the tension or the thickness allows you to sustain that additional pressure inside it. Similarly, when you have a liquid or specifically when you talk about liquid droplets, right? So liquid droplets are kind of, the reason they're spherical in shape often or curved shape is because of a similar idea, right? So now the liquid droplet will have actually higher pressure than the liquid outside, or the fluid outside, or the air atmospheric pressure, if you want to say, or pressure outside, right? And the reason it can sustain that is because now of tension created by, as a result of surface tension, because of how dissimilar forces acts, or the asymmetry occurs in the fluid interactions or interatomic forces experienced by fluids at the surface, right? So I just want you to take this conceptual understanding of how surface tension, or what results or what causes surface tension from an atomic scales or from the molecular or fundamental level. Couple of terminologies or types of flow that you'll encounter commonly in real life, but also specifically you'll come across a lot during the course, right? So the first thing talks about steady versus unsteady flow. So if we take the flow apart outside and ignore it for a bit, if we are just talking about steady versus unsteady problem or a property or a parameter, regardless of whatever field you're talking about, maybe it might be heat transfer, maybe it might be like steady and unsteady forces or stresses, or you can from solid mechanics, or if it's dynamics, we can talk about steady and unsteady motion, right? What does it come to mind when you say steady versus unsteady, right? When you're talking about something being steady and unsteady, you're trying to figure out if the property, or velocity or temperature or any other parameter that you're looking at or concerned with at a given point, so at a specific location or at a point, does that change with time, right? If it's not changing with time, it is a steady problem. So if it's like you're looking at a problem or a property, you can ask yourself a question: does it change with respect to time? And this part with respect to time is very important. If the answer is yes, it changes, then that's a steady problem or a steady parameter. But if it's not changing, then that's an unsteady problem or an unsteady parameter, right? So that's pretty much the gist of it, right? But this is something that students will mix up, or often mixes up, right? And so I'll give you an example to show where the mix-up or happens, right? So let's say if we are looking at a problem of a nozzle or a flow through a duct whose diameter is decreasing. So I'm creating a nozzle, so you have a flow at certain velocity v1, right? Now since it's getting squeezed, the flow is getting squeezed, the velocity will increase as it keeps on the area keeps on decreasing. So you have a higher velocity v2 at the outlet compared to the inlet, right? You can think of is as if you have a hose, if you want to spray, but if you want the spray to go further away, one of the easiest way you can do is squeeze down on the end of the hose, right? What you're doing is you're reducing the area, you have the same amount of mass of fluid coming in, right? And mass conservation dictates you cannot have accumulation of mass here, right? So you need to have mass going out, or total mass coming in should equal to total mass going out. And since the area has reduced, the only way it can happen is by increasing the velocity, right? We'll be looking into the exact how mathematically that comes across in later section, but I'm hoping at least intuitively this will come across to you, right? So if I want to draw a plot of velocity versus location, right, if this is my x direction, so in the front part of it you have a v1 velocity, at the end you have v2 velocity, and this v2 is greater than v1. Anywhere in between, right, you will have a velocity v3 which will be in between this v2 and v1, right? So essentially in this case it is linearly increasing, or at least it's increasing. So if I ask you what is the deal with the velocity or the flow in this nozzle, is this a steady problem? Is the velocity steady quantity, or is unsteady quantity since it's changing, right? Most students will end up saying, or often the confusion is people or students end up saying this is as an unsteady problem or an unsteady velocity, which is not the case, right? And this is what I want to emphasize, right? What we are talking about here is change with respect to time. The velocity or the parameter or the property can change with respect to space, right? That is in x and y and z direction, right? So spatially it can have changes, but as long as it's not changing with respect to time, it is still a steady problem. So this problem is still steady, and because, okay, v2, the reason is if you look at this location of outlet, you have a velocity v2, right? This is definitely different from the inlet velocity that you had of v1, right? But this, right, so but let's think of if you go and check this velocity using an instrument at time 1, t is equal to 0 seconds when it just started off, right? Or time t equal to 5 seconds. And then if you come back a minute later, right, will this velocity be the same or change, right? In theory, it is going to be the same as long as the velocity, incoming velocity is the same, right? It's not going to change, right? So even though time has passed, this velocity at this location has not changed. So that's part of the reason you have this given at a given point, right? So at a given point, this velocity is not changing with time, right? It's going to stay the constant, right? The only thing that is changing, the velocity is actually changing with space, right? So it's not changing with respect to time. So this is a steady problem. So this is what I want to emphasize, and some confusion that students have is the fact that when they are looking at a problem, you have to make sure that you are talking about or looking at if that property is changing with respect to time. So the time part is very important. It can change with space. Only if it changes with time will it be called an unsteady problem. If it is not changing with time, then that's a steady problem. So the next thing we have is something called a laminar and a turbulent flow. Probably you're familiar with this. So essentially, I'll start off with this video which shows air rising from a candle, right? So it's essentially basic convection current. So for this video, what they're using is something called as a Schlieren image. Right? Schlieren image allows you to see things that are generally not apparent to naked eye. So here, when you're looking at this flame, you can see there is a lower region where the flow is kind of uniform and straight, but as it rises up in this scenario, it kind of dwindles away, right? It becomes chaotic, right? So if you look at a problem, essentially, commonly if you look at a candle, right, if there is no air blowing from the side, if there's a flame, the air rising away up is generally kind of uniform up to a certain point, and then it becomes a bit chaotic, right? It kind of moves around in any given direction, and the direction even also constantly changes with time, right? So this region of uniform and smooth orderly flow, right, or this type of smooth orderly flow is called as a laminar flow. And this region where the fluid or the flow behaves chaotic and is always changing with time is called turbulent. And as a result, turbulent flow generally, by definition, because it's always changing with time and it's chaotic, it's unsteady in nature, right? The reason where kind of you need to be familiar, at least conceptually have an understanding of it, is because later down in the course we'll deal problems where we'll talk about, what happens if we calculate certain quantity in the case of a laminar flow? What happens if you calculate the quantity in case of turbulent flow, right? You'll see that you can do analytical calculation when it comes to laminar flow, but when it comes to turbulent flow, there is no direct way to do analytical calculations because of how chaotic it is, right? So there's no direct mathematical models. You have to use numerical simulations or empirical data from experiments. Okay, so when it comes to the first example, right, so essentially the problem says to consider a fluid layer between two very large parallel plates separated by a distance L1 is equal to 2 centimeters. Now these are some of the things that I mentioned in the beginning that I would expect every student to follow when they are doing homeworks or exam problems. Give me a sec, sorry. Yep, so the first thing would be I need to see schematics, right? So, and it will help you understand or at least visualize the problem better so you can solve it. So that's the whole objective here, right? So the first thing is you want to draw a schematic which is similar to a free body diagram, right? Essentially putting in a diagram form or a schematic or a sketch what has been asked in this problem, right? So it's saying you have two parallel plates which is infinitely long, right? So we're not concerned about the length. You have two very long parallel plates. They are separated by a certain distance, and this distance is 2 centimeters, right? The flow is steady, right? So it's not changing with time, and it's laminar, so things are uniform, right? And this flow is created by moving the top plate by a velocity of 3 meters per second, right? So the top plate is essentially moving with 3 meters per second, while this bottom plate is stationary, so it's fixed. So its velocity is 0, right? So assuming the velocity profile to be linear, what is the shear stress in the fluid if the viscosity is 0.29 kilograms per meter square, right? So essentially it's saying the velocity profile is linear. So as we talked about, because of no slip, on the top, if this is moving with a certain velocity v, the fluid right next to or touching the top plate will also move with the same velocity, 3 meters per second, right? And the fluid at the bottom will move at the same velocity, or should have the same velocity as the wall that it is touching, so that will be 0, right? So now that you have been told that the fluid is linear or velocity profile is linear, that means you have 2 points, 2 velocities, and the distribution has to be straight line or linear amongst it, right? So essentially the change in velocity between these two plates is linearly changing. So this is kind of the gist of what's happening, okay? On top, right, so a couple of things that are given to you, right? And that is, first, you have been given the top velocity. V top is 3 meters per second. The bottom velocity is stationary, so that is 0 meters per second. And you have been given the height or distance between the plates, that is 2 centimeters. And what I try to do is, so I don't make mistakes in units, since this is all in meters per second in SI units, I'll convert it right here to meters. So it's 0.02 meters. That's third. And the fourth thing that you have been given is the viscosity. Okay, so these are the quantities that have been given to you. Now what you have been asked to find is the shear stress in this fluid, right? So in this fluid that is in between these plates, right? What is the shear stress because of the shearing motion that you have, right? What is the shear stress as a result of that? Okay, so now that you have done schematic, given and find, the next thing that I always ask students to do is write the assumptions, right? So for this case, right, what is going to be your assumption? So a couple of things that have already been explicitly mentioned to you here is you're saying that the flow is steady, you're saying that the flow is laminar, you're saying that the velocity profile is linear, right? And for all the problems that you're looking at, you'll always be assuming continuum, right? We talked about that. That's one of the biggest assumptions you always make, right? You also assume that this velocity here of the fluid next to this is also not moving with any different is moving at the same speed as that of the wall, right? So you have the no slip condition, right? So if you want to write the assumptions, you can list them as first is a continuum assumption. You will have no slip at the boundaries, no slip velocity. You have been told that the problem, you're assuming that the problem is steady. It is laminar, and then the velocity profile is linear. Right. So the last thing you want to do before starting to solve is at least list out the laws or equations that you're using, right? In this case, the only equation that we have covered is that related with Newtonian fluids, right? Which is shear stress is equal to viscosity times the velocity gradient, du dy, right? So in this case, you have been given the velocity. So you have these two plates and you know how the velocity is varying between these two plates, right? So you know the velocity distribution, so velocity as a function of y, or at least you can compute it, right, knowing that it is linear. So if you know the velocity profile, then you can find the derivative to find the velocity gradient. You have been given the viscosity. So once you find the velocity gradient, you can multiply by viscosity to get the shear stress, right? So now once you, in order to solve the problem, the first thing you want to do is get the velocity profile. So how would you get the velocity profile in this case? That would be part of the question, right? So what do you have here? You have, if you want to plot this, you have, this is a linear velocity profile, right? So this equation is a linear equation that you have. How do you find a linear equation given that you know the quantities of velocity at the two different points? So hopefully people are aware of that a linear equation is given by y is equal to mx plus c. That is just from linear algebra. The other way to calculate it is, if you have 2 points that you know, is like y1 minus y2 is equal to m times x1 minus x2, right? There are a couple different ways of solving this, right? So the best way to do this is by first plotting it out, right? So okay, so if you were to plot this velocity profile out, such that you have velocity in your y-axis, so you're plotting velocity in y-axis, and the location or the height at different points of the channel in the x-axis, right? So we know the velocity at y is equal to 0, since we have this. What is the velocity at y is equal to 0? It is 0, right? And we know the velocity at y is equal to 0.02 meters is 3 meters per second. So we have these 2 points, right? So essentially your linear profile is something like this, right? Because you're assuming, or you have assumed, that it's a linear profile. Now all we are trying to do is find this equation for velocity, right? So essentially from the linear equation for a linear line, you know that y is equal to mx plus c. In this case, your y coordinate or y-axis is represented by the variable v. You have m, and your x-axis actually represents the distance in the y direction. So this is y plus c, right? If you plug in the values here, so if you plug in this first value, right, at y is equal to 0, you have 0 times m, v is 0, right? You have c. This relationship will give you that c, your constant, or your y-intercept is 0, right? Next, if you try to plug in the value at this second point, you'll see that v is 3 at the location m corresponding to 0.02, and your c, you already found out it is to be 0, right? So from this you'll get the slope of the line, which is 3 by 0.02, right? You could have also found this m by directly from this. Hopefully people know that the slope of a linear line, remember that it is rise over run, right? So it's this difference in the velocity here. So 3 minus 0 by the difference in the distance that you have traveled, so 0.02 minus 0. So this comes about to be the same value, right? So there are two different ways to do this. Right, now if you plug in into this excuse me, if you plug in into this equation here, you see you get the relationship of velocity profile for this velocity corresponding to this problem. So y is equal to, you know m, which is 3 by 0.02, y, right? So this is your relationship you get, or velocity profile you get, right? So essentially if you plug y is equal to 0, you get v is equal to 0. If you plug y is equal to 0.02, you get 3, and you can plug so on and so forth at every given point, right? So that's, now that you have the velocity profile, essentially velocity profile means velocity distribution, right? All you need to do is find the derivative du dy, or in this case it will be dv dy, right? So what will be the derivative of this dv dy? That is nothing but, actually you'll see it ends up being the slope. So this is just 3.002. Now if you have dv dy, that is the velocity gradient or the shear rate, we said in order to find the stress, all you need to do is multiply this by viscosity, right? And then you have the final shear stress. So now you you have been able to compute what the velocity gradient is, you have been given the viscosity, hence you know the shear stress, right? So that's as simple as that. Okay, now in order to clarify things, we'll go to the different problem, and this might be a bit more challenging, right? So we have increased the complexity of the problem a bit more, slightly, right? So like what I talked about, in every problem I would need you to follow that format, right? So the first thing I want you to do here is try to write the schematic. This will ensure that you're not missing anything, and it increases the likelihood of you solving the problem correctly. So you essentially have two concentric cylinders. So if you're looking at a cross section of it, you have two concentric cylinders, and it is 40 centimeters long. The outer diameter of the inner cylinder, so that is this diameter, is 12 centimeters, and the gap between these two cylinders is 0.15 centimeter, right? Now the inner cylinder is moving and being rotated at a speed of, or it has a revolutions or rotation per minute of 300 rpm, and the torque that is being measured here write it here. Torque measured at that inner cylinder comes out to be 1.8 Newton meters. The question is, you need to determine the viscosity of the fluid. Again, you're assuming a linear velocity profile, and essentially if it's not set, your outer cylinder is stationary. So outer cylinder is not moving, so it's fixed. Right? How do you go about solving this problem, right? So again, couple of things you want to do is, first you want to list out everything that is given. So you have been given the RPM, right? You have been given the torque, you have been given the diameter of inner cylinder, D1, you have been given the thickness or the gap, so let's do delta D, and let me see if we have been given anything else. And you have been given the length, right? You have been given the length of the rod. Okay, and what you have been asked is to find viscosity mu, right? If we go back and to what are the equations we can use, we realize we mainly have one relationship that we have learned so far, right? And that the main relationship is that the shear stress is viscosity times du dy, right? If you know the shear stress, right, you can find force. How do you find force from stress? Stress times area is force, right? And can anybody guess how do you find torque, right? The reason is a torque is given instead of force. So if you know force, torque is just force times the torque length or the movement arm, or in this case the radius about which the rotation happens. Okay, right? So you can see that you have been given the torque, you know some details about the geometry, so you need to find, you can find the force, right? So if you know the force, right, so if you know the force, you have the geometry, so you know that you can find area. So from force and area you can find stress. Once you know the stress, right, you have this relationship. You need to find what the velocity gradient is. If you know the velocity gradient and stress, you can find the viscosity, right? So this is kind of a backwards way of solving, and the reason we kind of are able to do is because we have listed out all the things that are given, all the things that we need to find out, and the equation that we have, right? So that allows us to visualize what needs to be done, right? So in order to use this relationship, right, about stress times du dy, stress is equal to mu times du dy, you need to know the velocity gradient. So you need to know some information of the velocity. Now the question is, how do you find velocity? You have not been explicitly given velocity, right? So this kind of goes back to how do you find velocity now that you know the rotations, right? So you have not been explicitly given velocity, but instead of velocity you have given how fast the cylinder is moving, right? So for hopefully students know how you can find linear velocity from revolutions per minute, right? RPMs is just saying number of revolutions, or essentially how many 360 degrees the cylinder is making every minute, right? That's revolution. One revolution 360 degrees. So how many of those revolutions you are making per minute, right? So what you can do for people who don't know this, right? So in order to find first, and I'll break it out down into step by step, right? So if you want to find angular velocity, you can do so by multiplying RPM by 2 pi, and this is nothing but literally describing what I said, right? Revolution is 360 degrees, so 2 pi is 360, and how many revolutions I'm making? That is n1, right? So you're making 360 times n1 turns per minute, right? So that gives you your angular velocity. Once you know your angular velocity, how do you compute your linear velocity? You get your linear velocity by multiplying that by r, right? So sorry, I should erase that. I mixed this up. So your linear velocity v1 is nothing but angular velocity times the radius r1, right? So you know n1, right? That is, n1 is 300 rpm, right? So you know omega 1, so you now have omega 1, you know r1. R1 has been given to you because you have been given the diameter, so you can multiply r1 with omega 1 and you get your linear velocity, right? Just make sure again that you might have situations like here you have mixed units, right? So if you're using everything in meters, then use in meters. If you're using part of it in meters and part in centimeters, don't mix them up. Or here in this case you have RPM, so remember this is revolutions per minute, not per second, right? So try to just be consistent. Okay, now that you know the linear velocity, right, now things becomes a bit more straightforward, right? Or you know the inner velocity, right? So essentially you're saying you have the cylinder, you know the linear velocity on the inside, and that comes about to be v1, while the outer velocity is 0, right? It's stationary. And we have said that essentially across this your velocity is changing linearly. So if you take a point and cross section along this, you'll see that the velocity is changing linearly from 0 to the value v1, right? So if that's the case, similar to what we did before, how do you find du dy, right? That is nothing but it comes about to be v1 minus 0 divided by this gap, right? So it's like the location of v1 y1 minus this y0 location, right? So essentially it ends up being v1 divided by the delta d that you had, right? So the thickness or the gap between these two cylinders, right? That will give you the velocity gradient or the change or slope of the velocity profile or the shear rate, right? These are all the same things. Now that you know du dy, right, you can go back to this relationship, right? You have tau is equal to mu du dy. So you have calculated the biggest challenge here, right? So that du dy was the biggest headache for you to calculate, right? Now we talked about that you have been given torque, right? And torque is force times the distance. So times the distance r1, right? So if you want to find force, you can just divide the given torque by r1, which is the inner diameter radius. Once you have the force, you can find stress or shear stress, that is tau, by dividing force by area, right? What is the area of the cylinder, right? So you have these two concentric cylinders, you have fluid in between them, right? So the area of the cylinder that is exposed to the fluid is the circumferential or the surface area of the cylinder, right? So this area of a cylinder, how can you find it, right? It is is pi r, I'm trying to think. Oh, sorry, that's my bad. I had said it correctly in the beginning. So area of a cylinder is the perimeter 2 pi r 1 in this case, because the torque that you have measured is in the inner cylinder. So you have considered with the area of the inner cylinder. 2 pi r1 is the perimeter times the length, right? You know r1, you know length, so you know the area, right? So you can divide this force by area to compute stress, right? So now you know this quantity stress as well, right? So if you divide stress by du dy, you get your viscosity, and that is what is asked from you, right? So this is actually the way viscosity of a material is, or a fluid medium is determined. You have a device similarly where you have a rotation, you have two cylinders, you can put liquid in between them. One of them is kept fixed with a sensor where you can measure the velocity and the RPM, or rather than velocity, is more easier to measure the RPM, and then you measure the force or torque experienced by that cylinder inside, and then you can use this basic linear assumption to calculate the viscosity as such, right? Okay, so we have gone through a couple of examples. I will be posting a homework by tomorrow related to this, and that will force you to apply this, right? It will be slightly different, it will be more challenging, but the point is it will force you to kind of apply and understand some of the concept, right? When I do problems, I know when it comes to students, they try to plug in numbers directly. I try to keep it in terms of variables, so that at least they see which terms or how each quantity was computed, right? If I plug in the number of the value or magnitude of force and area here, if you come back later or students don't remember, or it might be confusing, it's like, oh, what this 0.02, or where did you get this from, right? So by writing it out explicitly, I believe that helps explain things better, but there's another reason for it which we'll talk later during the course. This is more intuitive and gives more information because you can see the actual relationship that is there, right? And then I personally prefer to plug in the numbers at the end, right? Something you'll see me say multiple times, right? When it comes to exams or even homeworks, right? This course is not a math course, right? Right, you need math to be able to solve the problems, right? So I'm not looking at the final answer, the magnitude or the value of it, right? Because technically you are using calculators. Everybody, I'm hoping you can use calculators, right? So I don't check the final value, but what I emphasize is on what the steps are, right? So for me, the student knowing the steps is more important, and I want to see the steps in any homework you do or any exam problem you do, and I don't care about the final value, right? So you might get the final value right, but if all of your steps are wrong, then what's the point, right? Or vice versa. For me, you might have done some basic calculation mistake, and that's okay. You lose some points, but that will be like only a couple of points, right? If you have all your steps correct, you'll get 95% of the points for the problem, right? So as a result, I always want to focus on the steps itself. Okay, with that being said, when you start doing the homework problems, please, if you have challenges or if your concepts are not clear, please schedule with me an appointment for office hours so that we can cover it again. So finally, coming to the last part of just reviewing the topics covered here, right? So the first thing we did or we talked about was about continuum assumption, right? Where we said that properties of fluid, it is assumed to be varying continuously. That's literally where the name comes from, right? Continuum is coming from the fact that you're assuming the properties or parameters of a fluid varying continuously in space, right? And this is true when the system that you're looking at is considerably larger than the molecular length scales or the medium that you're looking at, right? So which is most of the cases that you're considering in this course at least. Okay, when it comes to properties of material, you can divide the properties into intensive property and extensive property. When it comes to intensive properties are properties that are independent, so it's not dependent on the size of the system or the mass of the system, right? So the best way I talked about is if you divide the system into two, will that property change? Or if you multiply or make the volume bigger, will the property change? If the property or parameter you're considering is not changing, as an example, density and temperature, then it's an intensive property. But if it changes, then it's an extensive property. An example is mass and momentum. Right. Now the next property, specific property that we were looking or specific with respect to fluids is that of viscosity, right? Viscosity or dynamic viscosity specifically is given by this letter mu, the Greek letter mu, and essentially it represents the internal resistance of a fluid to motion, right? So when it comes to Newtonian fluids are fluids that follow the standard relationship of shear stress is proportional to shear rate or the velocity gradient, that is du dy, and the proportional design is removed by this constant mu, right? Okay, so when it comes to shear rate, what I want to emphasize is the fact that the velocity changing or the slope that you're considering is in the normal direction, right? So be mindful of this. So for instance, here we use du dy that was specific to this problem, right? So you have x and y coordinates and this is moving with this velocity and you have a gradient in this direction, so yes, you use du dy, right? But now if I flip this and say I have two plates in this direction, right, and this is still my x and y coordinate, and this is moving with a velocity u, and this is stationary, so essentially you're getting a velocity gradient in this direction, right? So now you are not using du dy anymore, right? It is normal to the wall that you're considering. Your wall is this, so your velocity gradient is changing in this direction, right? So your shear rate is actually du dx in this case, right? Or if I write it more correctly, is dv dx, right? So just be mindful when you're talking about velocity gradient, it is the change in velocity normal to the wall, right? So if the wall is tilted, you have to understand that accordingly the velocity gradient you're looking at is also slightly different, right? So it's not going to be blindly du dy. So in general, you can say shear stress is viscosity times du dn, where n stands for normal direction. Okay, so shear rate is nothing but the change in velocity in normal direction. That is same as the slope of the velocity profile, right? Okay. So the next thing we want to do when it comes to this is we just talked about Newtonian fluids, right? So that's the one that follows this relationship. But there are other fluids which do not follow this relationship, and those are called as non-Newtonian, right? Okay. So when it comes to solving problems, right? We just did a few example problems. We know you probably realize that this is the only relationship that is new for you, right? You probably are already seen how force and stress are related. You are aware of that, how torque and forces are related. Those things you should probably know. So when it comes to problems related to this section, essentially the first job is to be able to find the velocity profile, right? Either it might be given to you or you need to find it out from the information that is provided in the problem, right? Once you know the velocity profile, you can find the shear rate by taking the derivative, right? So you can find the shear rate as a result, right? If you know the shear rate, then you can find the stress, right? Because if you have the shear rate, you multiply by viscosity, you can find the stress from this relationship. Once you know the stress, you can multiply the stress with area to find the force. If you know the force, you can multiply the force with the distance or the momentum or the radius if it's a cylinder to find the torque, right? So that's the way you go about it, right? So the key thing is, if you can find the velocity profile, then once you know the velocity profile, you can find shear rate by taking the first derivative in the direction normal to the wall, and then from the shear rate you can find the stress by multiplying it with viscosity. Okay, so that's essentially the steps that you need to probably be solving for most of the problems in this section. Okay, the next topic we kind of covered briefly was kinematic viscosity, which is nothing but dynamic viscosity divided by density. Couple of things that we discussed is how the viscosity depends with changes with temperature. So for a liquid, it decreases with increase in temperature, because when the viscosity decreases, you're saying the internal resistance has decreased, right? So a hotter liquid like oil or let's say honey will move more freely because the resistance has decreased, so the viscosity has decreased. But now if you make it colder, right, your resistance actually increases, so your viscosity increases, right? So it's inversely related. But when it comes to, I think that this is wrong, this should have been gas. So there's a typo here, so this should be gas. viscosity of gas increases with increase in temperature. Okay, so gas behaves opposite to liquids. That's the best way or easiest way to remember it. Okay, when it comes to surface tension, right, we kind of discussed a bit about this. The tension of the surface film of a liquid caused by the attraction of particles in the surface layer by the bulk liquid, which tends to minimize the surface area. That's the proper definition. What I want you to do at least is understand how it is generated conceptually. And that's like surface tension is the result of asymmetry in the interatomic forces acting on the liquid molecules on the surface. So we talked about this, right? Okay, so here I kind of go through the steps of solving the problem again, right? So first identify the velocity profile or velocity distribution. Once you know the equation of the velocity profile, this velocity distribution or velocity profile is nothing but equation of velocity or relationship for velocity. For V with respect to space, right? That's all that velocity distribution means. Once you know that, you can find the shear rate, which is the velocity gradient or deformation rate at a given point by either finding the slope of the velocity profile at the specified location. For a linear profile, this can be directly computed for all other profiles, right? So if it's not linear, you have to be mindful, and this is something that you will come across in the homework problem, right? So I'm leaving it for you guys to think of it. You need to take the derivative, right? So you can find this by taking the derivative du dn, which is in the direction normal to the velocity, right? So keep this in mind. N is the direction normal to the surface or the wall, right? So if the geometry is changed, the problem is slightly twisted, you have to change accordingly. Once you have the shear stress, you can just multiply with viscosity, find the shear. Once you have the shear rate, you can multiply viscosity to find the shear stress. And I've kind of made this note here. In general, your du dy is actually du dn. Right, so when you see this relationship du dy commonly being mentioned for Newtonian liquids, you'll see this often. In general, it means du dn. Right, they just go with a simple problem of a coed flow with the flow in the x direction, and that's the result. They use this relationship. Finally, if you know the stress, you can multiply by area to find the force. If you know the force, you can multiply the distance or the radius to find the torque, right? So that kind of goes through that problem again.